Hi, it's time for another math easy solution. To discuss a very interesting math topic, and that's looking at the point to line distance formula and looking at algebraic proof. And basically what I mean is the distance from a point to any given line. Now before I get to that specific proof, first what I want to do is recall the equation of a line, as well as the fact that a perpendicular line has a slope which is a negative reciprocal to the other line. And I've went over this in my earlier video on negative reciprocals, and you can see that in my earlier video for more detail. But basically if we have a line like this, so y-x axis like this, let's say we have a line such that is like this one is y equals to mx plus b, where m is the slope of the line, and then here's the slope is just rise over run m, so rise is 1, rise is m and run is 1, so m over 1 is just, well, m. Yeah, so that's just a line y equals mx plus b. And now if we have a perpendicular line to it, for example, let's say we have a line like this is perpendicular. I showed in my earlier video that this line is going to be y equals to mx, actually not mx, it's going to be the negative reciprocal, so we would go with negative 1 over mx, and I'll just call this b2. Let's say that's mb1. Yeah, so in other words, this rise over run, or the slope, is going to be, well, negative m over 1. I should have said, no, it's the other way around. This is going to be, rise is 1, negative m, like that. Yeah, so 1 over negative m, or to make it look more visual, because the line's going down like this, we just put a negative 1 over m, like that. And again, so then the negative reciprocal, if we have m, it flips, it becomes negative 1 over m, and this is the negative reciprocal, like this, reciprocal. And now this negative reciprocal is going to be pretty useful, because when we look at the distance from a point to a line, well, that's just that distance itself can be viewed as another line that's actually perpendicular to it. So we'll get to that's going to be useful when I go into the proof. So now the general equation of a line is written as follows. The most general one, instead of y equals mx plus b, it's ax plus by plus c equals to 0. This is the most general equation of a line. And then if you rearrange this, if you put this over to the other side and move this over and divide by b, what we end up having is, well, by equals to negative ax plus c, and then we could just divide by b on both sides, and then what we end up getting is y equals to negative ab, extend this past like that, x plus c over b. Yeah, so if this is the equation of a line like that, in this case we're going to have the slope is equal to this negative a over b, like that. And yeah, so here put this note as well, where a, b, and c are all just constants. Now if we wanted to find the shortest distance from a point to a line, we have 3 different scenarios we have to account for, and that is, number 1 is distance from a horizontal line. In other words, a equals to 0. So yeah, so if we have a equals to 0, then what we end up having is, if you look at here, this ax term goes away, so what we have is by plus c equals to 0. Rearrange this, we have, move the c over, we have y equals negative c divided by b, like that, and this is our equation of a line, y equals negative c over b, and this is just, well, constant. Yeah, so this is just constant. So in other words, the y value is constant for all values of x. If you were to draw this out, we get a horizontal line. So y like that, we just get a line like this, and this is our y equals to negative c over b. And now if we wanted to find out the distance to it, for example, let's say we had a point over here, and this point is p, and we'll call it xo, yo are the coordinates. Now the distance to it is going to be, well, just the line that's perpendicular. That's the shortest line to it. So this is going to be the distance d. And this is in fact perpendicular, so I'll just write like this, like that. Yeah, just remove the arrow. So that's perpendicular to it, and that distance is d. So then the distance d is just going to be the difference from the y values. So d equals to, well, y minus this one. That's the absolute value of it. So I'll just write y0 minus negative c over b. We could do the other way, but we have an absolute value, so it's going to be always positive. Now this equals 2, the negatives cancel, so we have now y0, I'll move this over because we can simplify, plus c over b like this. And a more useful way to write it is if we have times is b over b, so we have a common denominator. And now what we end up getting is equals to absolute value b y0 plus c, like this, absolute value all divided by the absolute value of b. And now the reason I write it like this will become more apparent later in the video, and that's d equals to that, like that. Because a more general derivation still works for horizontal or vertical lines, as I will show. Alright, so now let's look at the second scenario, and that's when the distance is from a vertical line. In other words, b is equal to 0. And again, if you look at that formula, if b is equal to 0, the by term goes away, and then what we end up having is an ax plus c, yeah, this would be 0, plus c equals to 0. So we have this. Yeah, so now when we just rearrange this formula, what we end up having is, well, the c goes on the other side, so we have x equals to negative c, then divide by a, so we have negative c over a, like that. And again, just like the other one, this is constant, like that. Yeah, so this means we have a vertical line. So the x is constant for all values of y. So we draw the xy axis like this, yx. So then we have a line such that is like this, where this line is x equals to negative c over a. It's always the same value. And now if we had a point here, and this is our point P, x0, y0, like that. Now this distance across is again going to be perpendicular to it, and we'll call this d. And now this is just the horizontal difference between the two. So in other words, d is equal to the absolute value, and you could just write it as x0 minus negative c over a. Or you could do the other way around, negative c over a minus xo, but we're doing absolute value, doesn't matter. So now this equals to, those negatives cancel, so we have the addition x0 plus c over a, absolute value, and again writing like this, so we can multiply a over a here, get the common denominator, and write it in terms of ax0, just as similar to the horizontal line one above. So plus c, absolute value, over absolute value of a, like that. And again, this will make more sense as I at the end of the video, to show you that it's the same for the general one for slanted lines, like this. And yeah, you can see the different or the similarities as well already. So axo plus c divided by a, absolute value of a, similar to this one here above for horizontal line, the distance between b, y0 plus c over absolute value of b, like that. Yeah, so now let's look at the distance from a slanted line, or a distance to a slanted line, i.e. when a and b are non-zero. And again, note, while this proof is not valid for a or b, for when a or b equals 0, because the negative reciprocals would involve dividing by 0 or by infinity, which are not defined, so we can't do that, as I will show in a bit. The final result nonetheless gives the same result for both horizontal and vertical lines as shown above here. These are actually the same result you would get using the formula, that the proof is not valid, but the end result is the same, which is very interesting indeed. So now the shortest distance from a point to a line is the line segment that is perpendicular to the line. Thus their slopes are negative reciprocals of each other. Yeah, so in other words, if we have an graph like this, x, y, and I'm going to draw a line like this, I'll call this line 1. This is line 1. And now this line has an equation, ax plus by plus c equals to 0. So that's the equation of a line. And then again, if we rearrange this, or we could write this as y equals 2, and then move this all around, we have negative ax minus c over b when we divide those out as I showed above. where this is the slope, negative a over b. In other words, we get a negative a over b, like that. Yeah, so that is the rise over run. So now, let's say we have a point here. I'll call this point P, like this, so I'll move it over. P, and this is x0, y0 are the coordinates. And now what we have is, let's say the perpendicular line is going to be somewhere like this. Actually, draw a bit better. So we have this point here, and I'll say at this point is at, I'll just call the coordinates x1, y1, like that. Now this line, I'm just going to call this line L2, and the distance from here to here, where this is a perpendicular line across it, this is going to be d. And now the slope is going to be the negative reciprocal of it, so we're going to have, if this is negative a over b, we're going to have b over a positive is going to be the slope, b, a. And likewise here, what we could do is draw a triangle, so to get a slope, the same one as the a over b, but with these given values of x1, y1, and xo, y1, like that. Like this. So we have this. Now this height difference is going to be y1 minus y0. This one right here is going to be x1 minus x0. Yeah, so now as I just showed above there, the slope of, I'll call this slope of L1, line 1 is going to be, well, negative a over b, like that. So then the slope of L2 has to be negative reciprocal equals to negative 1 over negative a over b, like that. And then what just happens is this becomes all positive, and then the b goes on top, equals to plus b over a, as shown over there. Yeah, so this is the slope of this line across there. And also, as explained above, also note that the slope of L2 is just a rise over run of the 2 points, and that is from, at this point right here to over there. And what we could do is just write, well, y1 minus 0, so I'll just write this here. So slope of L2 equals to rise over run, and the rise is equal to y1 minus y0 over x1 minus x0, which just equals to, well, this slope b over a, like that. So now we have an equation like this, and now what our goal is to do is to get rid of this x1 and y1, just so that we don't need to worry about where that point is at the perpendicular spot. And now what we have is, well, from Pythagoras, or the Pythagorean theorem, we could just, well, square that to get a distance. So distance is equal to d squared. Well, we have d squared is equal to, and now the difference, the difference in x, let's write difference in x1 squared, x0 of that triangle, and then plus y1 minus y0 squared, like this. So this is what we have, and here our goal is to get rid of this x1 and y1. Yeah, so now what we want to do is, well, find an expression for distance, as I explained above, that removes x1 and y1. And again, one way to go about this is to rearrange the above slope formula to maintain squared differences, because we have this y1 minus y0 and x1 minus x0, but now for the distance one we have squares. So we want to rearrange this and play around with it to maintain square differences, just like the distance formula, so we could eventually just plug in the d squared there and rearrange. So what we can do one way is, let's just write it down, y1 minus y0 over x1 minus x0 equals 2 b over a, like this. If we just move these across, just move these over and then move this on the other side, we get is an a y1 minus y0 equals to b x1 minus x0, and then just square both sides so we can get everything squared. And then what we end up getting is an a squared y1 minus y0 squared. Then we can just move this over to the other side, minus b squared x1 over x0 squared, and this equals to 0. Alright, so now that we have square differences, but in this formula it's not that useful, just right away to look at it. So note that this formula isn't that useful, but luckily there's another way to obtain squared differences. So another way is, well, again, multiply it out like that. So then what we have is a y1 minus y0 equals to b like this, b x1 minus x0, but instead I'm just going to move this over to this side. So what I'll do is put this as a negative equals to 0. So just move it over all in one step like that. And now what we could do here is, instead of doing the other way, we can just square this like that. And then square when you square this one, it's just, well, 0 squared is just 0. Yeah, let's put a 0 like this squared equals to 0. 0 times 0 is still 0. So now what we have here, if we square this out, just expand it using the FOIL method, we have a times y1 minus y0, then square that, so we have a squared y1 minus y0 like this, and then we can multiply this by this. We end up having a negative ab, and then x1 minus y0, y0 or y naught, x1 minus x0, not y, and then times by the y there, y1 minus y0. And then what we'll do now is multiply this by this. We're going to get the same ones, and it's still going to be negative, so we just add another 2. Let's do it to save time. And now with this one multiplied by itself, the negatives cancel. We have plus b squared times by x1 minus x0 squared equals to, well, 0. Yeah, so what we end up having is, if we move this over to the other side, we get a term that's going to be like this, a squared, oh, I forgot the squared there. Yeah, so yeah, I forgot the squared. So y1 minus y0 plus b squared x1 minus x0 squared equals to 2ab x1 minus x0 y1 minus y0. Yeah, now this term is more useful than the one above where it just equals 0. We have a difference like that. And the reason is because we have this 2ab x1 minus x0 and then this delta y term. Now this is actually very useful because we can obtain this 2ab term in multiple different methods. That's actually very amazing. Such as, so the one we did above here, we could do that one as number 1 is just the a, and also write delta y to just make it simpler, minus, that's this one above, b like this, and then this is going to be delta x like that. Yeah, delta x like this squared. So that's one way of obtaining that over there, and I'll just write this as delta y, and this one is delta x, just for reference. So that's one method. Another one is we can do it as, instead of subtracting, we can have it as a delta y plus b delta x like this squared. So this one, what we'll have is, if this times this, then we're going to have an ab delta x term, and then this by this, again, we'll have 2 of those there. So that's another method we can have. And in fact, we could see what happens. So this one above is this one here. So this one, I'll just write this as 1. That's the same one as over here. As we showed, is just going to be a squared delta y squared, and then we have a minus 2ab delta x delta y, and then finally plus b squared delta x squared like that. And likewise, we can go, if we do it this way, what we end up having is a squared delta y squared plus 2ab delta x delta y like that, plus right here b squared delta x squared like that. But what we have is this one a squared, and there's going to be a second one there. If we did it this method, we can have this term and then replace it with these ones over there. But one issue is that the a squared is a common factor of only the delta y, but not this one. But instead, what we could do is, well, switch the a and the b, or the delta x's. So switch this and this, and you'll see why we'll do that is, if we do that, if we have a delta x instead of a delta y plus like this squared, we end up having an a squared delta x squared plus 2ab delta x delta y plus b squared delta y, this is a y, delta y like this squared. Yeah, so thus if we had something like this, we could factor out the, for example in this one, the delta y squareds, and then we'll get an a squared plus b squared. And then when we do that with the delta x Same thing, when you factor this out, we get an a squared plus b squared, which is the same as that, and we can remove it altogether. Yeah, so as I just explained, thus if we use the third option, we can have a common factor of a squared plus b squared as shown below hashtag. Amazing, actually. So let's just go ahead and do that and remove this delta x's. So what we have is like this. If we had an a times it by x1 minus x0, and then plus, I'll just remove this for now, plus a b y1 minus y0, and then square, so let's say this one is equal to 0. Actually, never mind, we don't need the 0 part, we just square this. So if we square this, what we end up having is exactly as I stated above. This one times itself, a squared x1 minus x0 squared plus, and then this times this, ab x1 minus x0 y1 minus y0, and then this by this, we're going to have a second term of that, so 2, and then now we have plus, this times itself, b squared y1 minus y0. And now we have this term across there that is the same one as this one above here, which is equal to this, like that, and then we could replace this. So I'll write replace with above. So what then would we end up having is this equals to, put it like this, I should just move that over there. So now we have an a squared x1 minus x0 squared, and then scroll all the way up. So then now we have an a squared y1 minus y0, that equals to that term. So now we have a plus a squared y1 minus y0 squared, and it's a plus there as well, plus a b squared, and now we have an x1 minus x0 squared, like that, and finally over there plus plus b squared y1 minus y0. So notice what we have. We can take out the common factor of the a squared out, or actually instead of that we take the common factors of this one and this one out first. So then we have a squared plus b squared like this, and then x1 minus x0 squared. Now we take the a and the b out. Not the a, b. Now we take the y and the y like this, put an arrow so it's different. So now we have plus, again, same thing, a squared plus b squared when we factor it out, y1 minus y0 squared like this, and now we can factor out this. Absolutely amazing. So now we factor that out, we have an a squared plus b squared, and then we have an x, put a bracket like this, x1 minus x0 squared plus a y1 minus y0 squared like that. And now this one, we know what this one is. Remember this? This is just our distance formula squared. So scroll all the way back up. That's just d squared like that. Absolutely amazing. So we could just replace that with, so we could just replace this with d squared. So thus what we have is this one over there, that whole formula. So thus we have, put an arrow like this, so thus we have a squared, not a squared, we just have over there a delta x, like that, a x1, put that better, a x1 minus x0 plus b y1 minus y0, like this, and then this is squared, this equals to a squared plus b squared, and then d squared there. Absolutely amazing. And now we could also expand this one, so we can get another formulation. So expand, so we get a, inside this is going to be, when we expand this out, we get an ax1 minus ax0 plus, now this one, by1 minus by0, again squared, equals to a squared plus b squared d squared. And now we could just put these together, and then what we'll have is, I'll just write this as this. Let's put this one in the front, so we have a squared plus b squared. Then we have a d squared. Now when we look at this one, put those closer together, so we have an, or I'll put a bracket like this, yeah, like this. So we have an ax1 plus by1 minus an ax0 minus by0 all squared. And now what we'll note is that, notice this part right here. Yes, if I circle this one like that, I'll also circle it after. So note that the point x1, y1 is on the line. That's the cross section of the perpendicular lines on the line. So it's on the line ax plus by plus c equals to 0. And you could see that. Let's just go for a refresher. It's been a while. Let's see this. So there it is right there, x1, y1. It's on that line. Just remind you of that. Let's erase this. Alright, so yeah, put that back. Let's just go back here. So now that we know that, we could just plug that inside. So then what we end up having is an ax1 plus by1, and then plus c equals to 0. In other words, we could just move the c over to there, so we have a ax1 plus by1 equals to negative c, like that. Yeah, so this means we could replace this right here with c. So I'll put an arrow like this and plug that inside. So when we plug that inside, put this all down, what we end up having is an a squared plus b squared, and then d squared equals to, now we have a negative c like that. Yeah, so we have negative c, move it over, negative c, and I'll just move those, yeah, I'll move it after. So negative ax0 minus by0 squared. Now these are all negative. We could just take that negative out. So I'll put a negative, let's just put the negative outside of it. So we can have a bracket like this, negative, and then we have an ax0 plus by0, move it over on this side, plus c squared. When you square is negative, it just becomes positive. Yeah, so thus we just end up having is an a squared plus b squared d squared equals to, just move that whole negative out, ax0 plus by0 plus c, and then we square it all. Yeah, so thus we have, now we just move this over to the other side, and then we get square rooted. So we end up having is a d squared equals to ax0 plus by0 plus c squared over a squared plus b squared, like that. I'll just remove that bracket, we don't need it there. So now what we can do is just square both sides to get the distance. So thus distance d is equal to, it's equal to a number, it's plus or minus, but d is always positive, so we always have to go with the positive. So d is equal to positive square root, and actually no, the square root, yeah, the square root cancels with this one, so what we're left with is an absolute value of x0 plus by0 plus c, like that, over this one's just going to be square root of it. So square root a squared plus b squared is always going to be positive, and we always want an absolute value of the top part, like that. So there is the distance formula, like this, put it in the center here, so thus distance is equal to this. And now note, as explained above, this actually looks similar to the vertical and horizontal distances as explained above. So note that as explained above, this formula nonetheless works for distances to horizontal or vertical lines, even though the proof was not valid for them, because the negative reciprocals had, you know, a divide by infinity term. Because the slope of a vertical line is infinity, the slope of a horizontal line is 0, so you're going to have 1 over 0 or 1 over infinity, which is not defined. So what we have now is, well, for vertical line, so note for vertical line, this is when the x term goes away, so when a is equal to 0. So remember, the x term goes away, and the x term here would go away, yeah, so we'll have that b1 there. So remember this one, now the distance, if we plug that in, when we plug in a is equal to 0, what we get is, and actually I know when a equals 0, that's the x term goes away, we have y is equal to that. This is a horizontal line like that. Yeah, or distance to a horizontal line. Some places have it, they call the horizontal line that distance line. I like just doing it this way. Distance to horizontal line equals 0, and then we have d is going to be equal to, this goes away, so we have by0 plus c over this part here. The a goes away, so we're left with, well, square root b squared. In other words, we get absolute value of b y0 plus c, and we always needed absolute value, so what we get is absolute value of b. The square cancels, and this is this one like that. And again, that's the exact same as above. So now distance to vertical line, let's put this arrow like that. So this is when b is equal to 0, so the y term goes away, and we just have x equals to negative c over b over a. So what we have is, well, this term goes away, and then the b goes away, so what we're left with is d is equal to absolute value of a x0 plus c over square root a squared. Likewise, this is going to be equal to absolute value of a x0 plus c over a absolute value, like that. The squares cancel, and there is what we have. And then just to show you, that's the exact same one. Just look at this, b y0 plus c, and this one a x0 plus c. This one's divided by b, the other one's divided by a. And let's just scroll all the way back up so you can see that one again. Let's just see this a while ago. Yeah, so this is distance to a vertical line like that. So yeah, this distance to a vertical line, what we get is a horizontal line. That's, some places use it like that. I just like calling it like this. Distance to a vertical line, we get ax0 plus c divided by a. And then distance to a horizontal line, it's just going to be, it's exactly as shown above, as below and above here. So b y0 plus c over b. So yeah, very, very interesting. And I have one more note here. Yeah, so put a note here. So this is actually a great example of showing that we always need to apply mathematical rigor in our derivations, regardless of whether the end result will be the same, because not always will we be this lucky and may end up with large errors that build up. Hashtag life lessons for everything. Yeah, because that's the thing with math. You need to be rigorous. Even though the final result still works for vertical horizontal lines, they're still not defined by it, because of the way we proved this derivation. We used the negative reciprocal, or you're dividing by infinity or dividing by 0, so it doesn't apply to that. Yeah, because otherwise we're going to be dealing with limits, and you're going to have to work around it like that. For a even more general one, I believe there probably is one for that as well. So anyways, that's all for today. If you learned and follow along this pretty extensive derivation video, but very useful nonetheless, and I'll be using this in later videos. Anyways, that's all for today. Like always, you can download these exact notes in the link below, as well as viewing these notes on Steemit. And also make sure to check out my math forums and start posting whatever cool math or science related stuff you have. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.